welcome. We're starting this video. This is multiplication rule with a couple problems that were not in the last video, and you may have missed them in class. So, an 8-sided die has the numbers 1, 2, 3, 4, 5, 6, 7, 8. A spinner is evenly divided into 4 sections, black, green, blue, and purple. What's the probability of rolling a 4 and having the spinner land on black? These are independent events. The spinner could care less what the die rolled. Right? They have nothing to do with one another. So the probability of 4, that comma means then. It's the same as saying 4 with the intersection, black. Right? So where those intersect is the probability of getting a 4. There is 1 4 on our 8-sided dice. Right? So the probability would be 1/8. There is 1/4 of our spinner that is shaded black. So the probability would be 1/4. And then you just multiply the probabilities because there is 2 events. So if there's more than one event, you multiply the probabilities, right? And if there's more than one favorable outcome, you add the probabilities. But two events, multiply. So probability is 1/32. One other problem that we did yesterday, but you may have not have seen, and then we'll go into today's stuff. Probability of flipping a coin 4 times and getting all heads. These are independent events. One coin flip doesn't care what the others got. So the probability of heads, 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 there is 1 head out of 2 sides, right? So the probability each time is 1/2, and we just multiply those 4 probabilities together. 4 events, 4 probabilities, right? And we just multiply them. So probability is 1/16. All right, so today's stuff. And we're going to look at a dice problem as soon as I get to it. So this stuff is on the video, the second video on the Nearpod if you were absent in class, but this one is not, the one coming up. All right, 2 number cubes are rolled, 1 white and 1 yellow. Explain why the events are dependent and find the indicated probability. All right, so the yellow cube shows an even number and the sum is 5. Why would those be dependent events? So if I roll an even number for the first roll, what kind of number am I going to have to get for the second roll for that to add to 5? An odd roll, right? So an even roll on the, or even number, how about an even value? An even number on the first die, or cube, number cube, means the second die must show an odd number. And would just any odd number work? How about 5? 5 is an odd number. Could we roll an even number and then a 5 and have a sum of 5? That'd be too big, right? Can't get a 0, right? So the second die must be less than 5 to sum to 5. So we have some requirements here, right? That is due to the first die having an even number. Now this problem is not like the second problem. It is trickier. The other problem, we could just figure out the probability of getting a 6 and then times the probability of the other options that could go with the 6. Here, each value on the first die means a second value on the second die is going to be needed. All right, so when you've got a lot of different probabilities to figure out, your best shot is a probability tree, which I'm going to show you next. Everybody got this part up? Okay, we'll leave that up. You too, at home watching this, make sure you're writing this down. And we're just waiting for someone to finish writing it down, but she's working very quickly. Very hard to get that written down. I'm going to try to stay out of her way next time so she can write down the notes. Wait, none of you have to pause the tape because you have plenty of time to write these notes down. Yay, okay. You changed the page. Here is the probability tree. All right, and it shows our options here. All right, so even number, I could roll a 2, a 4, a 6. If we roll the 2, right, then we're going to need a 3 on the other dice to sum to 5. All right, so the probability of rolling the 2, there's 1, 2, 6 options on the dice, right? So the probability of rolling the 2 would be 1, 6. The probability of rolling the 3, 1, 3, 6 outcomes on a dice is also 1, 6. So the probability of 2 and then 3 would be 1, 6 times 1, 6, or 136. That looks a little messy. I'll rewrite it. Now we'll move this up. Ooh. All right. We could roll a 4. If we roll a 4, right, the probability of getting a 4 would be 1, 6 because there's 1, 4, 6 outcomes on the dice. If we roll a 4 to sum to a 5, we will have to roll a 1. So the probability of 4 and then 1 would be 1, 6 times 1, 6, or 136. Now we have 2 favorable outcomes here, and actually let's look at the very last outcome before we talk about that. What happens if I roll a 6 on the first die? Because that's a possibility, right? 6 is an even number. Well, if I roll a 6 on the even number, I have absolutely no options for the second dice because there's no -1 to sum to 5. So the probability here would be 1, 6 times 0 or 0. Right? There's no way you can roll a 6 and get a sum of 5. Now when we have more than one event, we multiply probabilities. So in this case, we had 2 rolls, right? We had to roll the one dice, and then we had to roll the other dice. Right? So 2 rolls in each outcome. That means we need to multiply, right, to find each probability. Right? So the probability of 2 and then 3, we multiply the individual probabilities. The probability of 4 and then 1, we multiply the individual probabilities, right? But what happens if we have more than one outcome? So if we have more than one favorable outcome, we add probabilities. All right, so here, the probability that we rolled an even number on the first die and then had a sum of 5 would be the probability, move that down here, would be the probability of getting 2 then 3 plus the probability of getting 4 then 1. Right? There's no worries about having to subtract anything because there's no overlap. These are mutually exclusive. So our probability is going to be 136 plus 136, which is 236, and that reduces to 1/18. Right? So here's one where we couldn't just multiply and get our answer. Right? We had to figure out each of the individual probabilities and then add those together because we had more than one favorable way to get a sum, have an even number and then a sum of 5. Any questions on this one? Right. So you have the nice little diagram. I drew it myself. Those are my little dots. In your notes, just add in the written part that I added. I think everything else is there. Right, so this was a good review of both addition rule and multiplication rule for independent events. The next part of the lesson, we're going to be looking at dependent events. Is everybody good? And you at home, if you didn't finish writing your notes, well, just pause the tape. And that's covered for a reason. We don't need that one. All right, so conditional probability often applies when data falls into categories. And we're going to have some notes for you to write in a moment. In many cases involving random selection, events are independent when there's replacement and dependent when there's not replacement. So fill in those two blanks. Not replacing the first item means there'll be fewer items to choose from, affecting the probability of the second selection. So the events are dependent. And then we're going to be working with some problems with a deck of cards. Remember, a deck of cards contains 4 suits. Each suit has 13 cards. Right? And the face cards are the jacks, the queens, and the kings. Every card, there's 4 of each kind. Right? There's the spade, the diamond, the club, and the heart. The four suits. Two cards are drawn from a deck of 52. Determine whether the events are independent or dependent. Selecting 2 hearts when the first card is replaced. Is that independent or dependent? Green 1. We're replacing the card, so it's just as many. Independent, right? If we don't change the sample set, it's independent. Right? So this is independent because the card was replaced. And these, I believe, are in your notes. All right, so we want to find the probability of a heart, and then the probability of a heart given that we got a heart on the first draw. And because we put the cards back, they're independent, so each probability will be exactly the same. What's the probability of getting a heart? Blue 1.
1/52 times.
How many hearts are there?
That's
Huh? 13. 13 hearts.
13
Right, so 13 out of 52. If we put the card back, what will be the probability for the second heart?
12 over.
We put it back, though. 13 over 52. Right. It won't change if you put the card back. We could reduce this. This would be 1/4 times 1/4, or 1/16. How about the second one? Selecting 2 hearts when the first card is not replaced. First of all, is that independent or dependent? Anybody have blue?
Dependent.
Dependent is correct. Right? The first card was not replaced. Right, so we just answered on the other problem, the probability of the first heart, right? So there are 13 hearts, 52 cards, right? That'll still be the probability for the first heart. But what about the probability of getting the second heart? Blue 4. What was the second number? 12 over?
Or 50. 1.
1, right? Yeah, 1 less card, right? So there's 1 less heart, 1 less card, right? So both of them reduced by 1. All right, so 13 over 52, that would be 1/4. 12 and 51 are both divisible by 3. So 12 divided by 3 is 4. 51 divided by 3 is 17. We could also cancel out these 4. So you're allowed to cross-reduce when you multiply. So our probability here is 1 out of 17. A little less likely, because I guess we didn't put the card back. We have 1 less card to choose from, but we also have 1 less heart. All right, let's do the third problem here. Still just the cards. A queen is drawn, is not replaced, and then a king is drawn. Independent or dependent? Green 4. And independent or dependent? Dependent. And we know this is dependent because the first card was not replaced. All right, so the probability of the queen is still 4 out of, excuse me. Yeah, 4 out of 52. A little better. All right, 4 queens, 52 cards. But how about the probability of the king, given the first card was a queen and we didn't put it back? Green 2. 4 over 51. There's still 4 kings, right? We didn't take any kings out, but now there's only 51 cards. So 4 out of 52 reduces to 1/13, and the 4 out of 51 doesn't reduce at all. So that's going to be 4 out of, like, so with the calculator, I think it's 668 or something like that.
663.
Ah, so close. 663. Oh, I should have realized. It ends 3 times 1. 663. I remember 2 out of 3. Everybody got those? Everybody good? Okay, let's do the next one. A bag contains 10 beads, 2 black, 3 white, and 5 red. A bead is selected at random. Determine whether the events are independent or dependent. Find the indicated probability. Selecting a white bead, replacing it, and then selecting a red bead. Independent or dependent? Red 4. Independent. Right, because the bead was replaced. Right, so let's find the probability of the white on the first draw and the red on the second draw. Right, what's the probability of getting the white bead? Anybody at red? 3 over 10. There are 3 white beads, 10 beads overall. How about the probability for the red bead? 5 out of 10, which will reduce to 1/2. Notice we didn't change the number of beads because there's still 10 beads. We put it back. So then this would be equal to 3/10 times 1/2, which is 3/20. The second one. Selecting a white bead, not replacing it, then selecting a red bead. Would those be independent events or dependent? Blue 3. Dependent, because we didn't put the bead back. Dependent, bead was not replaced. All right, we already answered the probability of the white. That was 3/10. That's not going to change. The first pick's not going to change. But how about the probability of the red, given that the first bead was white? Anybody at green? 5 over 9. Right, there's still 5 red beads, but now there's only 9 beads. And we could reduce that. Right, so we could reduce, you can cross-reduce when you multiply. So the 3 and the 9 are divisible by 3, so that'd be 1 and 3. And the 5 and the 10 are divisible by 5, so that would be 1 and 2. And that's going to give us 1/6. And then finally, selecting 3 non-red beads without replacement. Independent or dependent? Green 4. Independent or dependent? We're taking notes. Independent or dependent? What's that?
Is it the last one?
Yes.
Dependent.
Dependent. Right, we put the beads back. Right, we are taking notes, which means your notes need to be open. Dependent. Bead was replaced. All right, so the probability of a non-red bead. Blue 1.
7. Oh, I'm sorry.
5 out of
10.
10 beads. All right, we don't put the bead back. Now what's our probability?
This would be 4
Uh-huh.
over 9.
4 over 9. And we still don't put the bead back.
3 over 8.
3 over 8. So each time we have one less red bead and we have one less bead overall. All right, so we can do a little reducing here. That 5 tenths reduces to 1/2. So 1/2 times 4 ninths times 3 eighths. We could cancel out the 4 and the 8, or the 4 and the 2, whichever you like. 4 divided by 4 is 1. 8 divided by 4 is 2. The 3 and the 9, 3 divided by 3 is 1. 9 divided by 3 is 3. And so that will give us 1 in the numerator and 12 in the denominator. Half as likely as the question before. Any questions on these three? And we're just zooming along. Anybody need this? I'll leave this page up for a moment. You get home, take notes. And then we're going to look at a diagram that I think is mostly filled in. That we'll just talk about. And what it does is it sums up the different probabilities we've been looking at. Then we'll do a few more probability problems. The one problem, though, works so much nicer up here in color than it does in your notes in black and white. And you'll see that in a couple of slides. Right. Oh, before we go over that, I forgot. We have a couple questions that we'll do together. And then we're going to go over the diagram. I can see someone's notes, so that's why I knew there's a diagram coming up. All right, cookie jar contains chocolate chip cookies and oatmeal cookies. You take a delicious oatmeal cookie out of the jar and eat it. You then take a chocolate chip cookie out of the jar. What kinds of events are these? Mutually exclusive, independent, dependent, indirect. Blue 4. I take a delicious oatmeal cookie out of the jar. I eat it, and then I take a chocolate chip cookie. Dependent, yep. Right, you change the sample set. You can't put it back if you ate it, right? Mutually exclusive means things that can't happen at the same time, right? So things like spinning a 4 and spinning a 6, right? There's nothing in common between those. Rolling a dice and getting a 4 or getting a 1, right? Those are mutually exclusive. Independent means that our sample set would not be changed, and indirect has just nothing to do with probability whatsoever. Let's take a look at the next one. A cookie jar contains chocolate chip cookies and oatmeal cookies. You take a delicious oatmeal cookie out of the jar. Maybe you take a nibble out of it, a small nibble, and put it back. You then take a chocolate chip cookie out of the jar. What kinds of events are these? Green 1. Independent. All right, because you put it back. All right, maybe it has a little nibble out of it, but you put it back. So I got a funny story. I'll let it be on tape. So my mom, she used to buy, like the Valentine's Day, the heart-shaped boxes, and it would have the candies in it, right? But we didn't want to eat just any candy, you know, and you pick it up and it's the strawberry cream or the orange cream. So some of those we didn't like so much. And I don't like caramels because they're too chewy. So we would like pick at it, open it up, not that one. Pick at it, open it up, not that one. Pick at it, open it up, oh, that one, I'll eat that one. So those would be examples of independent events, because we didn't pick out the cookie. The first two were independent, right? Because we replaced the candy. Just had a little bit of a hole in it. And then my mom would look and she goes, "Why do all these candies have holes in them? Stop picking at the candies." She used to hate that. And both me and my sister did that. All right, here we go. Here's the diagram I was telling you about. All right, so this sums up mutually exclusive events, independent events, and conditional events, which are dependent events. All right, so we have mutually exclusive events have nothing in, oops, pen down, have nothing in common, right? So they I should say, they can't happen at the same time. Like on our spinner there, spinning a blue and then a green, right? They have no overlap, right? So if we're figuring out the probability of spinning a blue and then spinning a green, right? That would be just the, if we want to find the probability of spinning a blue and then a green, right? So two events, we would just multiply the two probabilities together, right? And because they are mutually exclusive, they are independent events, right? There's no overlap. It's just the each probability multiplied together, right? If we wanted to find the probability of blue or green, right, that would be addition, right? So blue then green is two events. Blue or green is two favorable outcomes, but one event, right? And we just add them together. No need to subtract because they are mutually exclusive, right? But what if we have events that are not mutually exclusive? They have overlap, right? Well, then when we find the probability of A or B, we add them together, but then we have to subtract off the probability of A and B. All right, so in my example here, the probability, these are independent events, but they're not mutually exclusive. The probability of A and B would be the product of those probabilities. Right? So the probability of A and B in my example here, I guess I can't point because nobody can tell where I'm pointing to on the video. Here, I'll have an arrow now. I'm pointing to this one. All right, we would just multiply to get the probabilities. If I wanted to find the probability of A or B, we would add the probabilities together, but since there's overlap, we have to subtract, right? Because they can occur at the same time. We subtract the probability of A and B, right? And so the probability of A or B would be 0.58. If they're mutually exclusive and there's no overlap, we don't have to worry about subtracting anything, right? Because there's no blue-green here. If we have conditional events, right, then the sample set has been changed. The probability of the first affects the probability of the second. So here in our example, I'm going to go over that one. I'm just going to stop my arrow over there. We have 4 red socks, 6 blue socks, 5 white socks. If we want to find the probability of picking a red sock and then a red sock, right, we would find the probability of the red sock, which there's 4 red socks, 15 overall, so the probability would be 4/15. For the second red sock, we've taken a red sock out, so now there's only 3 red socks. I can't seem to get the whole thing on. There we go, on the screen here. There's only 3 red socks now, right? And there's only 14 socks overall. So the probability of red and then red would be 4/15 times 3/14. We could reduce that. We could reduce the 4 and the 14. We could reduce the 3 and the 15. And the probability would be 1/35. So here, this diagram here just sums up all the different probabilities we've looked at. Right? Probability of this or that, where they're mutually exclusive or not mutually exclusive, and the probability of this and that when they're independent or dependent. Right? Any questions on that? Okay. You have seen pages twice? All right, so here we have a cookie jar. It contains 8 chocolate chip cookies and 4 delicious oatmeal cookies. You take a cookie out of the jar. The first cookie is for you to eat. The second cookie you take out of the jar you give to your dog. So you'll give him the chocolate chip cookie. The table below shows the cookies in the order they were taken out of the jar. So this is experimental probability. And for experimental probability, it's the favorable outcomes, however many favorable outcomes, whatever you deem is favorable. And then the denominator is the number of trials. All right, so we want to find the probability of chocolate chip cookie and then oatmeal cookie. All right, and so the order matters here, right? It asks for chocolate chip and then oatmeal, which is not the same as oatmeal and then chocolate chip. Right? Plus, you're eating the first one and giving the second one to your dog. So chocolate chip and oatmeal is different than oatmeal chocolate chip. How many favorable outcomes do we have here? Green 2. So how about in the first row? Do we have any favorable outcomes in this first row? Any of them say chocolate chip and then oatmeal?
You have one.
One, right? That one right there. Any favorables in the second row? Yeah. Any favorables in the third row? Not 3,
Oh, no,
just 2.
I read that. Yeah.
Any favorables in the fourth row?
No.
No. How about in the last row? 1. So how many favorable outcomes are there? 5. How many total trials were there?
Like
20, yeah. And that would reduce to 1/4. Right, so here's an example of experimental probability. This one is a compound probability. It's 2 events, right? Because we're picking 2 cookies. But in this case, because it's data, it's just favorable outcomes over the number of trials. I think one year this was a benchmark question, something like this. You have a jar with 4 red marbles, 5 green marbles, 2 blue marbles, and 6 purple marbles. You choose a marble and do not replace it. Then you choose another marble. Find the probability of blue marble, then purple marble, and explain your answer. All right, so very key here, we are not replacing it. All right, so we want to find the probability of blue and then purple, given we picked a blue marble. I think this one's in the notes. All right, so what would that probability be? Anybody at blue? So what's the probability of getting the blue marble? What was that? 2/17. There were 2 blue marbles, 17 total. And then how about the purple, given that we got the blue? Right, so we have 6 purple marbles, but now we only have 16 marbles overall. We can reduce that, so that would be 2 17s times 3 8s. And we could reduce that again. We could reduce the 2 and the 8. They're both divisible by 2, so that would be 1 and 4. So that would be 368. All right, so now the question also says, and explain your answer. So I'll let someone volunteer on this. So explain how we got the second probability. What happened in our second probability when we were finding the probability? What was that? So we didn't replace the marble. So there was 1 less marble in the sample set. How about the purple marbles? Were they affected? Yeah, they weren't affected. Right, so just the overall marbles. We have 1 less marble. Well, specifically 1 less blue marble. Let's look at the second question. There 3 marbles are picked. And again, we're not replacing it. What is the probability of choosing 3 green marbles in the row? So we want the probability of, I should probably write this in green. Yeah, since this should be a green question. So we want the probability of green, and then the probability of green, given we got green on the first pick, and then the probability of green, given that we got green on the second pick. Equals. All right, what's the probability of getting the first green marble? Blue 3.
5 out of 17.
How about the second green marble?
4 out of 16.
How about the third green marble?
3 out of 15.
Yep, so each time those marbles are decreasing, number of marbles decreasing, and the number of green marbles are decreasing. All right, so we can do a little reducing here. 5 out of 17 times 4 over 16 reduces to 1/4. 3 over 15 reduces to 1/5. And we could cancel those 5s. So that's going to give us 1 out of 68. So that was harder than the last one because this was only 1 out of 68. And the probability of blue then purple was 3 out of 68. Any questions on these two? Okay. All right, so this question works a little bit better up here than it does in your notes. I don't know if you've got a marker or can write, the colors over it. This would make more sense, I guess, or you can write the number of colors. All right, so a jar contains the following marbles. All right, so notice there's 5 red marbles, there's 4 green marbles, there's 3 blue marbles, and there's a black marble. And if anyone wants to grab Sharpies, I have Sharpies up there. How many of each? There are 5 red marbles, 4 green marbles, 3 blue marbles, and 1 black. All right, so what's the probability of selecting 2 red marbles if the first marble is not replaced? So we want the probability of red, and then, I should write that in red, shouldn't I? Make my ink match the marble. Probability of red, and then red given that we already got a red on the first pick. Anyone at green, what's the probability of getting the red?
5 over 15.
How about the second red?
4 out of 12.
4 out of 12. Right, 1 less red, 1 less marble. Right, and we can reduce the 4 out of 12. So 5 out of 13, 4 out of 12 reduces to 1/3. So that's going to be 5 out of 39. So now we want the probability that neither marble is green. I guess I shouldn't write in green, huh? So we want the probability of not green, and then not green, given we got a not green. All right, so anyone at red, what's the probability of not getting green?
10 out of 13.
There's 4 green marbles.
So it's 9 over 13.
No, 13. Assuming that there's 13 marbles. I never counted. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Good. 9 out of 13. And then what's the probability of getting the second non-green marble, given that you got a non-green marble on the first pick?
8 over 13.
You sure about the 8 over 13? If I take a marble out, will I still have the same number of marbles?
No, we're all
12,
12.
yeah. So we have 1 less non-green, 1 less marble overall. So that would be 9, I'm going to reduce here, 9 out of 13 times. 8's divisible by 4, that would be 2, and 12's divisible by 4, that would be 3. And we could reduce the 9 and the 3. 3 divided by 3 is 1, 9 divided by 3 is 3. So that's going to give us 6/13. Almost half. Any questions on that one? And might be at the end of what this tape's going to be. If it's conditional probability, using the formula, I think I'm going to stop right here. Let's see what this next one is, and then I'll know for sure. Oh, one more with, we'll do this one. Well, this will be our last problem. We'll do one last problem. Actually, you know what? We'll do this one in class because the numbers are really small. Oh, no, yeah, we'll do this one in class. We'll do it in class. We'll stop here because the first period didn't do it anyway. All right, well, we'll stop here and bye for now, and I'll see you in class tomorrow. Bye-bye.